So section, no, actually, I lied. This should be section 2.3. Ah, right. Yeah, we should probably start off with 2.3. All right, so section 2.3. Let's begin this way with the limit as x approaches 2 of the cube root of 12x plus 3. What would you do for something like this? How would you calculate that limit? Yeah, plug it in. First thing you should always try when working with limits is to plug in the limit. In this case, we get the cube root of 27, which is 3. Great, you're done. Don't overlook plugging in the limit, because a lot of times, not necessarily a lot of times, but sometimes it'll work. So let's take a look at one more, and it's really just to kind of remind you of some of your trigonometry. Again, the limit as x approaches 2, this time of the sine of pi x over 2. There's nothing wrong with plugging in the limit. You get the sine of pi times 2 over 2, or basically the sine of pi. What's the sine of pi? Y-coordinate at pi 0. Big goose egg. So these work out pretty nice because they're nice continuous functions, and you can just plug in the limit. Now, there's something that is even nicer about limits, and that is they kind of match our intuition. That's not always true with math. Sometimes there's things in math that you want to do, but you can't do. Here's a good one from algebra class that people want to do. People want to split up a square root and say, oh, well, that's a square root of 144 plus a square root of 25. Is it? Here I get the square root of 169, which is 13. Here I get 12 plus 5, and I'm thinking that those are different. You can't take the square root of a sum by taking the sum of the square roots. It doesn't work. But with limits, your intuition does help you out. There are things you can do that you think you can do, and it works out pretty nice. So let's flip over to page 79 in the book and see what some of these things are. So you've got two functions. Let me try and reposition this a little bit better. F of x has a limit of L. G of x has a limit of K. And what's this saying? It says, well, if you have not just the function, but a constant times the function, then you get the constant times the limit. If you add or subtract the functions, you add or subtract their limits. If you multiply the functions or divide the functions, you multiply and divide their limits. And a power, again, gives you the limit to a power. So these are things that you would like to think are true, and guess what? They are true. So these are some properties of limits we can and will use while evaluating our functions. So let's start out with, I think it's problem number 44, 42 or 44. Let me turn the page. So page 42. Let's start out there. Or not page 42. How about problem number 42? Problem 42, they give us that the limit as c approaches, or as x approaches c of f of x is 2. And at the same time, the limit as x approaches some constant c of g of x is 3/4. Then they're going to ask you a series of questions based on these limits. And I kind of like these problems because there's really not a whole lot in terms of calculations. It's just, do you understand some of the basic properties of limits? For instance, part A, the limit as x approaches c of 4 times f of x. So you have this new function which is 4 times f of x, but really that's not much different than the old function. If you want to be kind of really formal, you can factor the 4 out, and then you have 4 times the limit of f of x, but we know what that limit is, right? That limit is 2. So overall the limit is 8. I'm not sure I'd really actually demand that you show this step or not. I mean, I'm showing it because, later on it's helpful to move constants out of this and just focus on the function, but, either way, I think the answer should be pretty clear that that's an 8. Let's try a couple more here. Part B asks for the limit as x approaches c of f of x plus g of x. Any takers on that one? Yeah, thank you. 2 3/4. All right, so 2 plus 3/4, 2 3/4, or 11/4 if you want to show it as a improper fraction. But yeah, just add the limits. So our theorems are pretty nice. 2 more, the limit as x approaches c of f of x times g of x. And the limit as x approaches c of f of x divided by g of x. So see about simplifying, calculating both of those. Bonus points if you can do it without your calculator. Yeah, please.
What does the x approaching c mean underneath? Is that just a variable?
Well, x is your variable. C is some fixed number. Now, in the previous problem, x was approaching this constant 2. This is a constant, but it's an unnamed constant. It's just some arbitrary constant. But it's x is getting close to that. All right. So how about these two? What's this one approaching? 2 times 3/4 is 3/2. Good. What about 2 divided by 3/4? Good. Remember, you invert and multiply, so it's 2 times 4/3, or better yet, 8/3. 8/3 is in lowest terms. You don't have to write it as 2 2/3. I don't really care. As long as it's in lowest terms, that's good. Now let me share with you real briefly a little bit of insight as to why we're focusing on limits and where this course is going, etc. So what I've drawn here is just a little function, and we're looking at the function at 2 points. We're looking at the function at 0 and at 1. What you can do is calculate the slope of the line, and the slope of the line is going to tell you how the function is changing on average. Now, it's not necessarily changing at this rate at the endpoint here or the endpoint here, but on average, it's changing in accordance with this slope. Well, that's great, but sometimes we want to know not what's happening to the function on average. We want to know what's happening to the function like right now. So, kind of by comparison, back in the 50s, when police were trying to catch you speeding, what they used to do is they set out a couple air hoses on the road. And as you ran over the first air hose, time started, and you ran over the second air hose, time stopped, distance equals rate times time. They got your speed in that interval, and they could tell if you're speeding. Of course, if you're smart, what'd you do? Yeah, you hit the brakes. As soon as you saw that first hose, you hit the brakes, right? And so because they're getting kind of your average speed in that interval, well, maybe they didn't catch you speeding. So technology catches up with things, and now they got radar guns, which is more or less instantaneous. So same thing's happening here. This is the average change of the function. But sometimes we want to know what's happening instantaneously. So here's what we could do. Let's move this point closer to this one so that it's a better representation of what's happening at this point. So let me do that. Let's slide it closer. And now the average rate of change is getting to be a better and better approximation of the actual instantaneous rate of change. And closer and closer. And eventually, those 2 points come together. The fancy word is to coalesce. And now you've got the instantaneous rate of change. What's happening to the function at that instant? This instantaneous rate of change is something that you can get through the derivative. So our work with limits is to try and find the slope of the tangent line, which is what we have here, and that is measured by the derivative. So it's all fitting into a bigger picture. Now eventually with the derivative, there's going to be lots of applications of the derivative, maximizing and minimizing functions, optimization problems, and then eventually we're going to start doing the opposite of differentiation, which would be integration. And that's going to open up the door to more and more applications. So that's where we're going, and that's why we're focusing on all these limit problems right now and understanding limits, because the derivative is built on limits. Let's try a few more, kind of like problem 42, and that would be problem 44. Got to remind me, I always got to switch the views by going to the software. Somebody pointed out that some of my videos to date don't always quite follow along because you can't see things. So I got to switch with the software, not with the buttons up here. Problem 44, the limit as x approaches c of f of x is 27. Like the last one, there's 4 different problems that we need to calculate. Part A is the limit as x approaches c of the cube root of f of x. Part B, the limit as x approaches c of f of x divided by 18. Part C, the limit as x approaches c of f of x squared. So it's the whole thing squared. And last but not least, the limit as x approaches c of f of x to the 2/3 power. And we should be able to come up with a nice exact expression without using our calculators. You can if you want, though. See if you can do it without it. Okay, Natasha, how about the first one? What's that going to give us, please? Good. Cube root of 27 is 3. Nice. And Amelia, how about the one below that? So it's really, yeah, 27 divided by 18 in lowest terms is 3/2 or 1.5. Cool. Thank you. Jack, what's 27 squared? Good. 729. And last one, we need 27 to the 2/3 power. Now there's a little trick here that I show my algebra students. Maybe it'll help you out. And that is, it's sometimes helpful to convert this back to a radical. So we got 27 to the 2/3. I kind of jokingly call this the boot method. Draw a little boot here. If you kick that helpless little denominator and take out your aggressions on the subject of math, the 3 comes out in front, the 2 drops down, and we get the cube root of 27 squared. Now, how does that help us? It helps us because the smart way to do this would be to do the cube root part first. It's going to make this a smaller number. What's the cube root of 27? 3. But then I haven't used the squared. So 3 squared is 9. Done. You can get that off your calculator, but sometimes when people enter that into their calculator, they make mistakes. So it's nice to be able to calculate it exactly, especially when it's rigged to work out pretty nice as it was. Are we looking okay with those first two? All right. Now, if you look at the name of this section, it says Evaluating Limits Analytically. We had 3 different ways that we could evaluate limits that we discussed so far. Graphically, algebraically, and numerically with tables. So analytically, I kind of throw that in with algebraically, right? Or maybe I should put it the other way around. Algebraically, throw it in with analytically. I'm going to show you or go over again 3 different ways that you can, 3 different tricks that you can evaluate limits with. And we've seen them before, but I want to go over them some more and in some detail. Let's start out with the factoring. Problem number 46. The limit as x approaches negative 2 of 3x squared plus 5x minus 2 over x plus 2. Now, if you're like me, when I was a student, I was terrible at factoring these things. Boy, you put a coefficient in front of that x squared, I fold. That's it. I give up. But let's be a little bit careful and thoughtful about this. I guess, you know what, the first thing I should have done in working with this limit is what? Yeah, try plugging in the limit. Now, no surprise, you end up with 0 over 0. We should always try to plug in the limit, because sometimes it's going to work. All right, so what else? Well, it'd be nice if this thing's factored. Let me go out onto the limb and maybe guess that x plus 2 is a factor. What do you think? Is that a good guess? It's probably a reasonable guess. And then you can kind of reverse engineer the rest of it, right? For instance, in front of here, I need a 3x, because 3x times x will give me the x squared. What do I need for the second part of this? Well, I have to have a 2 times something gives me negative 2. Not much choice there, right? So, wow. You should double check it by foiling. 3x squared minus 1x plus 6x. Well, that's my 5x, and then I get the minus 2. So it does check. It works. And then we can get rid of that term. And that was what was causing the problem. That's why we had a 0 over 0, is because when you put in that negative 2, you're going to get 0 in the numerator and in the denominator. That helps us out immensely. Now what should I do? Yeah, plug in the limit. Absolutely. So 3 times negative 2 minus 1 is negative 7. Done. But the trick in this one was to factor. Any follow-up on problem 46 here? Looking good on that one? Yes? If you try putting in the number originally, you'd end up with 0 over 0. Well, if you cancel it out here, and if you show me some of the cancellation, that's fine. But I like to see some of your work, because oftentimes you can get the right answer doing the wrong thing. And I get uncomfortable. So, yeah. Was there a question in back here? No. Good. Yes?
So factoring, you knew that in the numerator x plus 2 was going to be...
That was a guess. It was a guess because we're being cynical and know that these things are always rigged. So it was a guess. If you want to be really formal about it, let me remind you of synthetic division. The numerator has a root at -2. So put a -2 out in front here. The coefficients are 3, 5, and -2. Bring this down, 3. -2 times 3 is -6. Add is -1. Multiply gives you a +2. Add gives you a 0. So this is, the other factor. That's your 3x minus 1. And then by having a -2 out there, I had x plus 2 was my other factor. So that's kind of a very formal way to do it. And you can do it that way, but I don't often show this because it's been a while since most of you have seen synthetic division. But if you want to go look it up again, it's handy. Synthetic division. Yeah, it's definitely a handy little trick. Let's try one more with factoring. That's going to be number 50, unless there's some more comments or thoughts on that one. So number 50 is the limit as x approaches 0 of e to the 2x minus 1 over e to the x minus 1. Boy, that doesn't look like you're going to be able to factor that at all. But before we even get to that stage, you should check to make sure that you can't just get away with substituting it in. But when you try and substitute it in, you get e to the 0, which is 1. 1 minus 1 is 0. And that happens in both the numerator and denominator. So, bummer. How on earth are you going to factor something like that? Well, it's not necessarily easy to see, but this fits the pattern of a squared minus b squared. How does a squared minus b squared factor? Thank you. A plus b times a minus b. The trick is being able to look at that and realize that that's really something squared. E to the 2x is really e to the x squared. Because when you remove the parentheses here, you end up multiplying the exponents. So this is my a squared minus b squared here. A in this case would be e to the 2 or e to the x. What's b going to equal? 1. Limit as x approaches 0, e to the x minus 1. Somebody factor that for me. There you go. E to the x minus 1 times e to the x plus 1. So like I said, it takes a little bit of finesse to look at that and realize that that's a difference of squares. But after we catch that, well, then life gets pretty easy. That cancels. We're left with the limit as x approaches 0 of e to the x plus 1, 2. What's that limit going to equal? Yeah, 2. Exactly. 1 plus 1, get a limit of 2. Thank you. Now, what if I was looking at that and going, I'm not so sure I'm comfortable with that result. What else could I do to kind of prove that result to myself? Yeah, throw it in your calculator. You could plot it on Desmos. One of those things. So let's take a quick look at it on Desmos. So as you get close to 2 from the left Excuse me, as you get close to 0 from the left, you're getting close to 2. At 0 itself, the function is undefined. That's okay. But as you come in from the right, again, you're getting close to 2. So it's a nice confirmation that we've got the right limit. And I encourage you to kind of do things like that, look back at the limit, etc., make sure that you've got the right thing. Okay. There were some other types of tricks that we can use as well. One of them, and I think we've used this one before, and one example of it is to multiply by the conjugate. So multiply by the conjugate. An example using that would be problem number 58. This is going to be your one and only example like this. We did one like this the other day, though. The limit as x approaches 3 of the square root of x plus 1 minus 2 over x minus 3. Okay. Well, where should we start out? Yep. Well, let's see. Actually, where I was thinking was plug in the limit, but the limit turns into 0 over 0. All right, shocker there. Well, not really. So the next thing then is to multiply by the conjugate. Somebody back here, whose voice I didn't recognize yet. Yes, Philip. Yeah, hit it right on the head. We're going to multiply by the conjugate. So in this case, this is going to be the conjugate of the numerator. Limit as x approaches 3, square root of x plus 1 minus 2. The conjugate of that is the square root of x plus 1 plus 2. Now, you could, since you have a binomial times a binomial, you could FOIL that out. But that would probably mean you're going to end up working harder than I want to see you working. Let's try and do a little bit of finesse. This is my a minus b. This is my a plus b. When I multiply a minus b times a plus b, what do I get? A squared minus b squared. So rather than FOILing it all out, let's just kind of go with the shortcut here. Perfect. If you take a and square it, you're going to get x plus 1. So x plus 1 minus 2 squared, which is 4. In the denominator, I'm going to leave things just as they are. I'm not going to multiply this out. If you subtract, we're going to get the limit as x approaches 3 of x minus 3 over x minus 3 times the square root of x plus 1 plus 2. Okay. And finally, that x minus 3 term that was giving us the problems vanishes. We can cancel it out. It's not important as far as calculating the limit. The limit as x approaches 3 of 1 over the square root of x plus 1 plus 2. What's that limit? 1/4. Hey, 1/4. So that's a nice example of using the conjugate to help clean things up and get at the limit. Yes?
So for every line, you have to rewrite the limit.
That's a great question. On every line, do I have to rewrite limit? The answer is yes. Because in a lot of instances, not necessarily, yeah. In a lot of instances, some of these things wouldn't be true if you didn't have a limit. For instance, if I didn't have the limit on these last lines, this does not equal this unless you take the limit. That's the only time that that's true. So it's a good question. I really struggle with it when I grade your papers, what to do with people who just write all the algebra but forget the calculus. That is, forget to write limits there. It makes me uncomfortable, and I don't know. I'd suggest that you write limit near all these things. Charlie?
So we can't just write on the first and the last line, like where we circle it?
It takes you like 2 seconds, right? There's a kind of what I always say is keep your instructor happy, right? I got to grade like 60 of these things, so yeah, just keep me happy. I'm not saying that I'm going to take and mark off like 10 points out of 11 on a problem like this, but look, you want to get as many points as possible. Maybe I won't take off any, but the best bet is just to put them there, because that's formally what is true and what is happening. Let's try one last little trick here in terms of calculating some limits. That is to simplify complex fractions. Simplify complex fractions. Complex fractions are fractions that have fractions within their fractions. For instance, like problem number 62. Now, we actually did one like this the other day, but we'll do another one today. In fact, maybe two. The limit as x approaches 0 of 1 over x plus 4 minus 1 over 4 divided by x. Now, it's a good thing to prove that your answer is right in more than one way. So, to start this off, let's calculate it numerically. Let's see that we can get a numerical answer and then compare that to the answer that we get in this analytic fashion. So what we'll do is we'll put that into our calculator. Go to the equation editor, press y equals. Now I'm going to enter this in without trying to use any of the fancy math type that you can use on the 84 plus. And to do that, I'm going to need parentheses around the entire numerator. So we'll start out with a left parenthesis, 1 divided by parenthesis x plus 4, close parenthesis. Now that closes off the parenthesis in the denominator, minus 1 divided by 4. You can use 0.25, that works as well, divided by x. All right, from here, let's hit the second key, then the window key, or the graph key, and type in some values that are getting close to, where's our limit? Our limit is going close to 0. So what will be a sequence of values that are getting close to 0? 0.1, 0.01, 0.001, 0.0001, etc. And it seems like these things are settling down at about 0.0625. Now, keep in mind that this column of your calculator only can display 4 digits, maybe 5 or so, if you don't have decimals and negatives. If you want to see the exact value, just cursor over there. So if you cursor over there on the bottom row of your calculator, you'll see all the digits. At least all the digits that your calculator is willing to display you. It actually has a couple that it keeps in its hip pocket there. It's not showing you, but there are a couple there. In any case, it looks like it's settling down around negative 0.0625. Most of us probably don't recognize what fraction that is. That's okay. We'll compare it later. For now, let's work with simplifying the limit. And hopefully we get something that turns out to be negative 0.0625. This is a complex fraction. Let me write the x in the denominator as x over 1, just out of convenience. So this is your primary fraction. You've got a numerator and a denominator. And these are secondary fractions. I've put parentheses around all the denominators of the secondary fractions. The trick in simplifying these things is to multiply every term here by the LCD of the secondary fractions. So, what's the lowest common denominator for all my denominators in yellow? Good. 4 times x plus 4. So everything has to get multiplied by that LCD. And you know what? Just to be clear, let me rewrite it. You don't have to. In fact, if I were you, I'd write the LCD next to each of these. 1 over x plus 4 minus 1 over 4, x over 1. So the LCD is just really the product of these two. It's going to be 4 times x plus 4. 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 Looks good. The nice thing is that we're going to get some cancellation. So, the question is, what's going to cancel? Well, right here, the x plus 4 cancels. Over here, the 4 cancels. Do I get any cancellation in the denominator? No. So, limit as x approaches 0 of 4 minus x plus 4 over x times 4, I'll put the 4 out in front, times x plus 4. The nice thing is we got rid of the complex part of this. There's no fractions within fractions anymore. If you distribute the negative to both of these terms, we're going to get yet some more cancellation. The 4s are going to cancel out. What's left in this fraction? Yeah, just a negative x. So negative x in the numerator. We've come a long ways. If you try to plug in x equals 0 at this point, is that going to work? Can we plug in x equals 0? No. Yeah, we got to cancel the x first. Because right now, you'd still end up with 0 over 0. That's because we have this term here with a factor with a root at 0 in the denominator and in the numerator. But if you cancel that, we're going to get the limit as x approaches 0 of negative 1 over 4 times x plus 4. What's that limit? So negative 1 divided by 16. If you compare that on your calculator, negative 1 divided by 16, that's your negative 0.0625 that we saw from our tables. So, okay, good. Makes sense out of what we saw from our tables. You don't have to recognize this number. It should come out in the limit. How are we looking on problem 62? Okay there? So I'm going to give you guys a chance to work on something a little bit similar. So, last chance for, some help on something that I might have gone over too fast. Problem 76. The limit as x approaches pi over 4 of 1 minus a tangent of x over sine of x minus cosine of x. Trevon, what should we do first? Yeah, try plugging in pi over 4. Any guesses as to what's going to happen? Yeah, 0 over 0, exactly. So that's not going to work. If you recall, I called this section simplifying complex fractions, but I don't see a complex fraction here. Does anyone see the complex fraction? Where is it?
Tan of x.
Ah, good job. Tangent of x is really sine of x over cosine of x. So you got to clean this up by getting rid of the complex fraction here. And that's going to be multiplying by the common denominator and simplifying. So work your way through that. I'll walk around and try and help out. If you have some questions, try and grab a hold of me. If you're watching this at home, fast forward until that pause disappears. heard people say good things about them. I haven't pulled the trigger on them yet. Yeah. Okay. They look pretty comfortable. Okay. So let's take a look at this one. There's really only one denominator, right? It's cosine of x. So your lowest common denominator is just cosine of x. So I'm going to multiply the numerator and denominator by cosine of x. Can I get rid of this? I don't want that. There we go. I'm not sure what happened there. So I'm going to multiply the numerator and denominator by cosine of x. Cosine of x. Now when I do that, I'm going to leave the denominator by itself. I'm not going to mess with it. So it's going to be the limit as x approaches pi over 4 of cosine of x times sine of x minus cosine of x. All right, so I changed the order a little bit, but multiplication is commutative. In the numerator, I get cosine of x minus sine of x, because this and this are going to cancel. Well, it's looking better, but I've learned over the years that you guys aren't familiar with or aren't comfortable with one of the tricks that I use here. So let's just make this very, very clear. This and this look pretty similar. The only difference is the order here. And I can fix that if I factor out a negative 1. If I factor out a negative 1, this becomes sine of x minus cosine of x. And you can verify that if you distribute the negative to double check. If I distribute the negative, I get a negative sine of x. Negative times a negative is a positive cosine of x. So what's the benefit of that? Why did I do that? Yeah, so I can do the mother of all cancellations, right? Nice little ole there. Cancel out both of them. That leaves me with the limit as x approaches pi over 4 of negative 1 over the cosine of x. Finally, I can plug in the limit. Cosine of pi over 4. There's a couple different ways to think of it. Most of you are probably thinking of root 2 over 2, and that's fine. If you multiply negative 1 by the reciprocal, I get negative 2 over root 2. And that's not bad. I would suggest that you rationalize this. You rationalize it by multiplying by what? Root 2 over root 2. That gives me negative 2 root 2 over the square root of 4, which is 2. And finally, the 2's cancel, leaves me with negative square root of 2. Had you thought of this originally up here as, negative 1 over 1 divided by the square root of 2, then it simplifies to this right away. But most people, myself included, think of cosine as being root 2 over 2. Yes? Oh, if you left off the... See, this is why I want you to show your work. If you forgot the subtraction sign, all right, it's just a point, all right? It's not a big mistake, as long as, the rest of it's looking pretty good. So it's really to your advantage to show me your work, because the more of your work I can see and follow, the better I'm able to give you partial credit. Someone was asking about one the other day, and let's go back to problem 58. I'm not sure who it was, but I heard somebody, no, it wasn't 58, it was 62 here. Somebody accidentally added these two instead of multiplying. So they got negative 1/8 instead of negative 1/16. If I'm following along their work, I can see that. But suppose all I see is the answer of negative 1/8. It's wrong. And I can't give partial credit even if I wanted to. So, like I said, it's in your best interest to show me some of your work, because then I can give you as much partial credit as possible. We're looking okay on 76? Yes.
Yeah, I'm just confused at the taking out of the negative one, because at first I didn't even realize you needed to, so I paused the one, but it's
Okay. And I'm glad you mentioned that, because one thing that is, tempting for some students to do is to cancel here. Like, ooh, I can cancel the cosine x and cancel the sine of x. You can't do that. The reason you can't do that is that technically, when you're adding, subtracting those things, those terms are joined together. And what I say about these things to my algebra class is that these are married. If you break up a marriage, I'm going to write homewrecker all over your test. All right? Don't be a homewrecker. You can't cancel into an addition or a subtraction. So if you noticed, I didn't cancel into that. I factored out the negative and I canceled the whole thing. So I canceled the whole binomial term. I didn't just cut into it. And that's something you're going to have to watch out for. I guarantee that kind of mistake will be made before the semester's out. But, hopefully not too often.
you take out the negative one, you switch the sign.
Yeah, there's a few steps there to really show fully all the work. But, yeah, if you factor out a negative one from both of those terms, it flips the order. That's the shortcut. Good question. Anything else on 76? There's a few what are called special limits that you need to know. Mostly because you probably don't want to derive these things yourself. So, special limits. The good news is that you don't have to derive these things yourself. I'm giving them to you, and anytime you see them, you can use them freely. The first one is this. It's the limit as x approaches 0 of the sine of x over x. And that limit is 1. Which is kind of strange, because both of those are going to 0, and they go to 0 at roughly the same speed. So that's why you get a limit of 1. Another limit as x approaches 0 is 1 minus cosine of x over x. And that limit is 0. And what that's saying is that the numerator is getting close to 0 faster than the denominator. And so overall, the ratio is still going to 0. The last one, much different than the other two. The limit as x approaches 0 of 1 plus x to the 1 over x has the unlikely value, or surprising value, of e. E is in the base of the natural logarithm, is in the number that you use to help calculate continuously compounded interest. So that e. And that's going to play an important role for us later. But right now, these three limits are limits that you should know. So memorize these. And wherever you see them, you can use them. You don't have to prove this. With what you know right now, the proof of this is kind of difficult. Basically, they sandwich this between a couple different values and say, well, gee, both those values are going to 1, so that the limit must go to 1. It's a geometric proof. It's kind of a pain. In Calc 2, the proof of this becomes a one-liner. All right, so where are we going to use this stuff? Problems like 68. Yes?
When you plug in the limit, don't you have a 0 in the denominator? That bad?
Yeah, you end up with 0 over 0 here, but you can calculate this limit in other ways and show that that limit is 1. And so what I'm saying is that I'm giving that to you. That's something that you can use. Anytime you run across that limit, just plug in a 1 there. So, for example, problem number 68. 3 times 1 minus cosine of x divided by x. Now, if you wanted to be kind of very formal about it, you could take the 3 out in front. That'd be 3 times the limit as x approaches 0 of 1 minus cosine of x over x. But here's where I can use something that I gave you. I know this limit, right? Effectively, that's 3 times 0, which is 0. And that's the nice shortcut that you can take once you have those limits memorized, is that you can just plug in the value. You don't have to derive it. You just have to know what that limit is. So Giselle, does that help answer your question? What we want to do with those limits? You're just going to use them. You know that. I plugged it in here. 3 times 0 give me 0.
The thing I'm confused about is in other problems that you say, oh, just plug in the limit in the very beginning. You said it's 0 over 0. Therefore, it doesn't work.
I see what you're saying. Maybe I should say plug in the result, not plug in the limit. How about that? Because we're using the result. The result of this limit is 0. So we're plugging in the result. So that's where we got the 3 times 0 is 0. We're not, you're right. If I plugged in the limit, I'd end up with 0 over 0. And I'd be like, well, wait a minute, what's that? But you can calculate this and demonstrate this limit in other ways. And you can calculate and show that that limit is 0. So you're going to use the result here. All right, so maybe I'm not being very careful by saying plug in the limit. I should say plug in the result. Problem number 70. The limit as theta approaches 0 of the cosine of theta times the tangent of theta over theta. Good question. I mean, if you wrote 1 on the test right here, I'd probably be a little unhappy. There's one step I want to see here. What's that one step? There you go. Thanks, gentlemen. This is the limit as theta approaches 0 of the cosine of theta times the sine of theta over the cosine of theta divided by theta. And the nice thing is that the cosines cancel each other out. That simplifies this to the limit as theta approaches 0 of the sine of theta over theta. And what's the result of that? 1. Yes. So again, just using the results that were given up above.
No, just to clarify, so say for 68, instead of 1 minus cosine x, if that were just the sine, so it was 3 times sine of x over x, we would just do 3 times 1?
Yeah, exactly. That's exactly right. So that's how I want you to use these things. If this was 3 times sine of x over x, then over here I'd have 3 times 1, which would be 3. So, perfect. Let's try problem number 74. So in problem 74, you're going to learn yet another Greek letter. This is the limit as phi approaches pi. So after you finish this course successfully, you can apply to the registrar for 1 credit worth of a foreign language. That would be Greek. So certainly you pick up a lot of Greek letters in math. Limit of phi times the secant of phi. Wow. What are we going to do with that one? All right, phi is, or secant of phi is 1 over cosine. So this is the limit as phi approaches pi of phi over cosine of phi. Okay, I'm good with that. Now what? Noah? Close. Yeah. Plug in the limit, right? That's what I've always said. Always, always, always. The first thing to try is to plug in the limit. And there's nothing wrong with plugging in the limit here. You get pi over cosine of pi. And cosine of pi happens to be -1. So overall, the ratio is negative pi. But don't overlook plugging in the limit. Sometimes you'll strike pay dirt. Sometimes it's going to work. Anything else for kind of the wrap up on section 2.3? We're looking good there? For homework. Try 5 through 35, and I put a little note underneath here. EOO. I've never had a class yet that's missed figuring out what that is. Every other odd, yeah. That cuts down your homework tremendously. It's like do every fourth problem, basically. So every other odd, just for those. Now, if you need more practice, go ahead and do it. 37 through 47, 51 through 61, 67 through 79. Now, in 79 itself, see example 10 in your book. Like I mentioned earlier, I can't always give you examples of every single problem that you're going to face in the book, so here's one of them. But take a look at example 10 from the book.